Thank you very much, Dima, for your introduction. And I wanted to tell you that it's a real pleasure to be here. I think last time I was here, when was our last meeting, Alvaro? I think it must have been 2018. 2019. It looked more because I was really missing the institute. And then we had a couple of meetings, virtual meetings. But before that, once we organized a DMRG workshop. It's a workshop that has the Eschers drawing with the birds crossing and with the metamorphosis of the birds. The Steve White was here. I mean, I really enjoyed that DMRG workshop we had. So, I mean, I feel at home here. I like the Institute very much. I really thank you also for inviting me, and I'm very happy also to be able to contribute to the Institute from the advisory committee. Thank you for coming. I know there's a variety of different fields here. I'm going to try not to rush too much with the basic concepts of condensed matter, but what my main message today, I want to show you some emergent phenomena. Yesterday, David spoke about fundamental physics and also about different scales. And this is something I want to talk to you about, but from the point of view of condensed matter. So I think it's a good thing David spoke about that yesterday, because we can compare different approaches from condensed matter and from high energy physics. I want to talk to you about this emergent phenomena. I want to tell you about charge and spin separation, about the formation of quasi-particles. I won't be able to talk to you about so many different interests in physics in condensed matter that arise due to strong correlations. But I'll give you a couple of examples to give you a flavor of how interesting it is when strong correlations are dominating our systems. So this is why I put that this is the quantum condensed matters of playground for emergent phenomena and complexity, which makes it very interesting. So this is a photo of where I am in Bariloche. This is the lake. And now at these moments, there are many, many Brazilians in Bariloche, because it's really like an invasion of Brazilians, and we call it Brasiloche. So let me begin by thanking my collaborators in this particular topic, Gabi Kotler, Marcelo Rosenberg, mainly in the topics that have to do with DMFT, dynamic and mean field theory. I'll mention something about that. Please stop me, because I might use some jargon, and please interrupt me when you need. Masatoshi Imada in Tokyo, then Daniel Garcia, Pablo Cornaglia in Bariloche. We also have some results with Eduardo Miranda, mainly also in DMFT many years ago. And then my former student, Uriel Núñez Fernández from Cuba. Uriel is responsible for all the coding. He liked coding much more than physics, and it was very difficult to bring him down to think about physics, because he wanted to optimize the codes, and he was very good. So he left us really very optimized codes in Bariloche. Armando Aligia, and then Rubén Huet, that works with DFT. We're collaborating in Buenos Aires, and also my students Nair and Hernan, who's also from Cuba. So what is the concept of emergence? I like this idea. I spoke about this several years ago when I gave a colloquium here, but I just want to get the concept again to show new results we have. What is emergent physics? Emergent phenomena, says the US National Academies, in condensed matter and material physics, are those phenomena that cannot be understood with models that treat the motions of the individual particles within the material independently. Instead, the essence of emergent phenomena lies in the complex interactions between many particles that result in the diverse behavior and often unpredictable collective motion of many particles. That means the total is much more than the sum of individual particles. Like Phil Anderson said it, and he wrote in his book, more is different. When we have more, is different than calculating the physics of individual particles and then trying to predict the behavior. There's something new physics that emerges due to the interaction between these particles. Yes. Correlations, interactions, Coulomb interactions, magnetic interactions, any interactions, anything that takes us away from the one-body physics. Okay, so now this is all the problems I'm facing. I'm going to show you today are impossible to calculate starting from the one body physics like we do in the tight binding model, for example. We cannot just diagonalize a system for one body and then fill the system with other particles, because the particles start interacting between themselves, and that turns it a complex, an exponentially complex system. I go back to that. So the reduction, so this is, Phil Anderson said in his book More is Different, and also in Science he published it. The reductionist hypothesis, that means reducing, like high energy physics, like particle physicists like to do. So I have my husband is a particle physicist, and we have fierce discussions with him because he's a reductionist. He says fundamental physics is really fundamental particles. And I said, no, I mean, our quasi-particles with the dressed electrons we have here are as fundamental as your quarks. That's what we think. So Phil says the reductionist hypothesis does not by any means imply a constructionist one. That the ability to reduce everything to simple fundamental laws does not imply the ability to start from those fundamental laws and reconstruct the universe. It's impossible to reconstruct the universe or even a solid from quarks. And Bob Laughlin said, everything that matters in science now is organizational. It has to do with organization, with how we treat information. The reductionist fundamental approach has stopped from being useful. It's not useful. At every scale of physics, we have to find the appropriate laws at that particular scale. It's not a lack of computational resources. It's a way, epistemological way of how we do physics. And here are some examples. For example, materials with strongly correlated electrons, strongly interacting electrons. This is the whole world of many body physics, because you cannot reduce everything to the calculation of one body. And here are some examples. For example, Fermi and non-Fermi liquids in low dimensions and close to quantum critical points. We have a phenomenon like the fractionalization of the electron. When we have interactions, and I'll show you, we can have the phenomenon of charge and spin separation. So the electron charge is not anymore, it does not have the quantum numbers E and spin 1/2, but the charge can have its own dynamics, and its spin can have its own dynamics. So we can separate the quantum numbers of a single electron. We can also find magnetic monopoles. We can also find that, for example, a system with spin 1, a Haldane chain, we can find fractional excitations of spin 1/2 in a purely spin 1 chain. Okay, so this is called fractionalization. How is it that we can find excitations of spin 1/2 when the only component we have is spin 1? And this happens at the open boundaries of, this is a topological effect. Then we can also find examples in broken symmetry phases and with hidden order, like, for example, liquid crystals. I'm talking about emergent phenomena, phases with topological order, like the fractionalization of charge. Here in the fractional quantum Hall effect, we also find the fractionalization of charge. The electron does not have a charge E, but can have E/2, E/3, and this has been observed, that the charge is a fractional value of E when there are strong interactions. Also, the fractionalization of spin orbit and magnetic monopoles. For example, this is in the interacting system. You can really separate the positive and negative poles of a magnetic excitation in a system. Okay, so the magnetic monopoles do exist in interacting system. Superconductivity and superfluidity, so the quantum coherent states, are also an emergent phenomena. Then we have critical phenomena, scale invariance in systems. The scale invariance is independent of the microscopic components. So you go, when you look at vortices, for example, you have a scale invariance, and so then you can change the different scales and explain the phenomenon with renormalization. And this, we heard about that quite a lot yesterday with David. And then cold atoms, they have metal insulator transition. This is also, we can have an insulator not only with a band insulator, we have an even number of electrons, but we can also have an insulator with an odd number of particles, with one particle per site, for example, in a system. And how is it? Because the band is half filled, but due to interactions, we can observe a metal to insulator transition. The system gets rigid and it becomes an insulator. And then quasiparticles, and I show you some quasiparticles that with of the type of excitonic quasiparticles or hole-on-doublon quasiparticles. A very simple example of the fractionalization of electron into charge and spin separation. This happens in one dimension in systems like this, for example, strontium, copper, oxygen. In this paper, and one can think about it in the following way. This is the system, a one-dimensional chain, and here it's half filled, so we have particles up and down, and they are antiferromagnetically coupled. So then if we do a photo emission experiment and we come with a photon and we eject an electron, we create a hole. This hole is a positive charge. And then now this hole is going to have its own dynamics, which is separate from the dynamics of the spin. So here we're going to have a hole which has a separation between its charge H and its spin S. Because, for example, the hole can hop like this to the right, and to the left we have this two parallel spins, which is a spin excitation, because it's an excitation compared to the antiferromagnetic background. And due to antiferromagnetic quantum spin fluctuations, this ferromagnetic bond can move independently to the left. So here we have an independent spin excitation from a charge excitation. This is a cartoon of what is called the spin charge separation. We did many years ago when I was doing my PhD, so it's in the prehistory, with Carlos Balseiro and a collaborator, Eduardo Jagla. We did a very simple calculation to observe the charge and spin separation. So this is using Langshows, exact diagonalization. We have the Hallberg model in one dimension. It's a closed ring. We have hop-in, we have local U. And the ring is very small. It only has 16 sites. So this is the site. And for the case, non-interacting case, this is a tight binding. You must have seen in Introduction to Solid State Theory. For U equals 0, so no interaction, only hop-in. At time the system has 3 particles, and at time t equals 0, we add 1/4 particle. In the form, we add a particle like this. This is a Gaussian wave packet, and the bottom is a spin density, and the top is a charge density calculated like this. And then, of course, if we add it with a certain average momentum to the right, k, this moves in time, so time is when we go down, so we see that both charge and spin move together. You see they evolve together. They separate a bit because the dispersion relation is not linear, so there is, I mean, if it were linear, it wouldn't disperse, but as is a cosine, it disperses, and then, but you see the charge and spin are exactly one on top of the other. When we put a very large U, we do the same, but we see that the top goes faster. This is the charge. The charge is going faster than the spin. There is an interaction, so they're not exact quasiparticles of the system, but they are very well, a very good approximation. And the charge is already getting to the border and comes in through the other side, while the spin moved only a couple of sites. So the charge velocity is much larger than the spin velocity. Okay, and this can be compared to exact results, to Bethe ansatz, and to the results of Haldane and Schultz. So this was funny, and then I show this because a couple of years ago, even Google calculated this with its supercomputer, with quantum computer, sorry. So with Google Sycamore, which is a quantum computer built by Google that has very few qubits, it has about, I mean, they simulated a linear system with about 16 qubits, but then they have hundreds of qubits to reduce the noise. But they're able to simulate certain phenomena, so they generated a quantum number. And remember this paper where they said they had this quantum supremacy. With that word they're using, that they achieved quantum supremacy because they could generate a quantum number in a few seconds they generate a random number in a few seconds, where if you want to do that with a classical computer, it would take, they say, hundreds of years. But then IBM people came and they said, no, it's not hundreds of years, it's several days. But in any case, they have this quantum computer working, the Sycamore. And this quantum computing is a lattice. The qubits are superconducting fluxes with Josephson junctions. So each one of these crosses is a qubit. So what did they do? They simulated a charge and spin separation. They cite us in this paper, but I think it was never published. So nobody in Google was worrying to publish the paper. But they also do the same. They have a linear chain. Each of these sites is the 2 qubits, because it's a Hallberg model, and the Hallberg model is a superposition of 2 qubits per site, because you have up, down, and 0 and up, down. And so then they plot the charge and the spin correlation, and all this is measured with quantum gates. And then, as you see here, the charge is the blue and the spin is the red. They don't have a finite k, but they produce a centered wave packet, like a Gaussian, and then it spreads to the sides. So you see that the charge is spreading faster than the spin, and they get this charge and spin separation for a large interaction U in this system. This was interesting because this is done with a quantum computer. And then there are other papers where they use cold atoms, and they also show charge and spin separation with cold fermions in 1 dimension. Another example of a very complex system with interactions are high TC. Which is still not understood, and not even the normal state. Yesterday, we had a talk by Marino where it was interesting to see that people are still thinking, because it's not solved. So the high TC really catalyzed research in systems with strong interactions. So many groups started working, and many body systems. So this is really, it has a fascinating behavior, and many groups started thinking, and even with the improvement of computers now, we can understand things better, but it's still not solved. We still don't know what the mechanism of TC, of the high TC is. So this has to do with complexity. What is complexity? The complexity is when the numbers of degrees of freedom, they grow exponentially with the system size. So this means that as it is exponentially complex, one must optimize the information. We cannot keep all the information, because then we cannot go to very large systems. We really have to trim. We have to throw states away, and this is optimizing information somehow. And so what we do is quantum optimization using quantum information, and this is a density matrix normalization group. So what is the idea behind this? Where is this? So this is this is a Cayley tree where it has so many ramifications, and this is exponential. So let's think about what is exponential complexity, the Heisenberg model. One dimension Heisenberg model, these are spins 1/2, and this is S dot S. So here you have SZ times SZ plus S plus S minus plus S minus S plus. You have quantum fluctuations. So this is a complex interacting quantum system. So if we have it in 1 dimension, we have n sites. In each site, we have 2 degrees of freedom. The spin can be up or down. So these are the eigenvalues of the Pauli matrix of SZ. Okay, so we have 2 here, and this is 2. So then we have 2 to the n different states in this system. So if you want to draw all the different configurations of this, you have 2 to the n states. If we have 4 sites, we have 2 to the 4 different configurations. Up, 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 up. Then you put 1 down, and you have the 4 different configurations, etc. Until you get. So there are 2 to the n different configurations in this. So that makes it exponentially, because if I go to larger n, the number of states grows exponentially with the number of sites. And so now, if you want to do exact diagonalization, you need to diagonalize matrices that are of the size of 2 to the n of 2 to the n. So this is really very large. And currently, one can diagonalize matrices that correspond to about 18 or 20 sites for a Heisenberg model and not more than that. So imagine now if we have a Hubbard model, it means that we can, this is one site in the Hubbard, no, not even. In the Hubbard model, for every site we have M0, up, down, or up, down. We have 4 degrees of freedom. So the number of states goes like 4 to the n in the Hubbard. And if you want to look at more orbitals, it's even worse. So really, very quickly, it becomes exponentially complex. So what do we do? Now, I like this John Preskill's idea he expressed in the year 2000 when people were thinking about quantum information to distill or to optimize information in these systems. There's a new perspective on quantum mechanics. So he says, John Preskill, the most challenging and interesting problems in quantum dynamics involve the understanding the behavior of strongly coupled many-body systems. Better ways of characterizing the features of many-particle entanglement may lead to new and more effective methods for understanding the dynamical behavior of complex quantum systems. So he says we need to think of better ways for characterizing the many-particle entanglement, and how do we? That has to do with quantum information. So then came a group of people with Gaite, Latorre, Ignacio Cirac, Frank Verstraete, Osborne, and many others that really they were coming from the quantum information group and optics, and they came into condensed matter, and it was very profitable. So this is the old version of what the DMRG is, because Steve White in 1992, so before the quantum information perspective, Steve White was, he was excellent in doing research using quantum Monte Carlo, etc. But then he came up with a method that he called the density matrix normalization group. That is the following: you have a system. The system. This is for example the 20 sites of my spin of my Heisenberg chain. I divide the system in 2. And I call the right part of my system per se, and the left part I call it the environment. So I'm creating an environment which is not a thermal environment; it's a quantum environment, but with the same Hamiltonian of the system. And this was the genius of Steve. And then when I cut it in 2, I can define the density matrix. The density matrix means it's a trace. Let's see, I define the ground state of this whole system. I partition the function. I can define now a density matrix, which is the trace of the ground state, the trace over all these environment degrees of freedom. And that means that I have a matrix on this. This is a matrix on this side, and that matrix gives you information on the states on the projection of the wave function on this part of the system. Now, if I get the density matrix defined here and I diagonalize it, it has many eigenvalues. The sum of all the eigenvalues is 1 because it's a density matrix. But the eigenvalues give me the probability of finding the corresponding eigenvector in that ground state. So how do I choose the most relevant states? I keep the states with the eigenvectors of the density matrix with the highest eigenvalues. That's the way of choosing the most probable states. I throw away all the rest because it's not important to keep the 2 to the n states, because most of the states are irrelevant. Well, I only keep a very small fraction, 10 to the 4th fraction of the whole Hilbert space, and that turns out to be enough for most of the system. Mainly if they have local Hamiltonians. In the local Hamiltonians, one can really choose a very optimized basis. So then once I've chosen the most relevant states, I can add 2 sides to the system. I grow the system, I do it bigger. Now I'm working in a reduced space, reduced and rotated. So as I reduce, it's not unitary anymore. I can't go back. Now I have this system. It's larger. Here, this one is only keeping the most relevant states. I do the same. I partition the function. I define the density matrix to the right. I diagonalize it. I stay with the highest eigenvalue states, and then I grow the system. So this is the basic behind the DMRG. But now things have evolved, and now the DMRG looks like this. And this is a graphic way of representing what is called MPS and MPO. This is jargon. MPS is matrix product states, and an MPO is matrix product operator. So what you do is you represent a wave function as a product of matrices. These are different sides, and these are matrices on different sides. And then when you multiply all these matrices and you trace, you get a wave function. I mean, it's a way of representing. It has to do with what is called now tensor networks, because it's a network of tensors. It's not only matrices, but they can have the mathematical form of a tensor. So now, if you think that I won't go into details, but if you think now that a wave function can be written as an MPS, just an example for you not to get lost with the MPS. You all know a dimer state. A dimer state means that we have for example, we have a singlet here, we have a singlet here. This is a dimer state, okay? This means that here we have, this state means up, down, minus down, up in these two sides, 1, 2, and the same here and here. This is an exact MPS because if I can really, this is side 1 and 2, and this is times, this is 3, 4, the singlet up, down, minus down, up in 3, 4, etc. So this is this times this times this times this. This is an exact MPS state. In a similar way, if you know the AKLT, Affleck-Kennedy-Lieb-Tasaki model, which is also an eigenstate of a special Hamiltonian for spins 1. So there are concrete examples that are really MPSs. Now, when you have more entanglement, because this does not have entanglement, I mean, if I cut the system here, the entanglement between left and right is 0. If I cut the system, depending where I cut, if I cut the system here between left and right, this is maximum entanglement because here I'm cutting a singlet. So I mean, so it depends on where I cut the system. So these are the concepts that we are using for the DMRG. Now, let's think we have the wave function written like an MPS. Now I can, what I'm going to do is I'm going to minimize the mean value of the energy because the DMRG is a variational technique. So what I do is I put arbitrary matrices. Then I calculate this object, which is the Hamiltonian sandwich, the mean value of the ground state divided normalized. So this sandwich is this over this. You see, I mean, the denominator is the ground state. I mean, the state times the state. This is the product of the state with itself. Okay, and then in the numerator we have the Hamiltonian is the product of these operators, and these operators are contracted to the top with a wave function and to the bottom with a wave function. So this mean value, we have to minimize this object here. And this is another way of doing, I mean, you have to go right and left and you go optimizing the states you stay with. Yes? No, it's not necessarily unique because if you have, I mean, if the system has is degenerate, it won't be unique. What you can prove is that by minimizing this, it's exactly the same as using the density matrix. I'm not using the density matrix here. I'm minimizing this beast here. But one can prove, because of the mathematical properties of the density matrix, that is the density matrix gives you the minimum of this object when you're truncating the space. And it is an SVD decomposition, a singular value decomposition of the system. And you can really show mathematically that this minimization is similar to keeping the highest angular values of the density matrix, and it exists because there is one minimum. We are using this minimization, I mean, in this form here. There are several, yes, you're right. I mean, we're using this. That means that this is a particular partition of the function, and we already have these matrices, but then we minimize this sector here. Once we minimize this sector, then we go to the right and we come to the left, and we do this. Then there's another way Steve White came up with, not adding two sides, but adding only one side. There are some variations of this method. I don't know if you mean other methods, Giuseppe. Yes. In that case, it's very difficult because you have a very highly degenerate ground state or nearly degenerate, and then you have to be very careful with what states to stay with. And people have not been using the DMRG for spin glasses because it doesn't work very well. Because it works best when you have a gap in the system. So that's why all the papers with DMRG were applied onto spin 1 chains, because they have a gap. And then, and it also works best for systems that do not have, that are not highly entangled. So if I have a one-dimensional chain with, for example, long range interactions, this is highly entangled. So when I partition the function, one can calculate what is called the quantum entropy, the von Neumann entropy of the system. So it's equivalent. It's the same as the same definition as the thermodynamic entropy, but it's at t equals 0, so it has to do with the degree of entanglement of the system. I mean, if you study quantum information, you can define the if I cut this here, for example, this system, I cut it here, then I can define the density matrix to the left and to the right. They have the same range, and when I diagonalize a density matrix, these eigenvalues omega alpha, I can define the quantum entropy between left and right. The quantum entropy here is the sum over all these alpha, or all these degrees, all these eigenvalues of omega alpha times log of omega alpha minus. This definition has to do with the eigenvalues of the density matrix. So the lower the entanglement, the better the DMRG works. I say entanglement because when the state is pure, entanglement is equal to the entropy. It's not valid when you have a mixed state. I mean, well, these are technical things. If you're interested, I can. So now, what do we want to do? I want to go a little bit to physics and to show you what we've been calculating with this. We want to look at materials with strongly correlated electrons. Okay, so as I said, high temperature superconductivity, multi-insulators, magnetic orders, etc., heavy fermion behavior, etc. So we want to apply our methods to systems where they have several bands, because I mean, in one dimension or in higher dimensions, there are many systems that are interested within the strongly correlated family. And here are some examples, but there are many. Iron-based superconductors, transition metal oxides like ruthenides, manganites, the VO2, helium-3 bilayers. I mean, these are atomic systems. 4F and 5F rare earth, heavy fermion materials, uranium, plutonium compounds. I mean, these are among the most complex materials to study, and there's no analytical way of studying these materials because interactions are very strong. So you cannot use perturbation theory. It's very difficult to calculate Green's functions. So you really, now we have to resort to numerical calculations, and numerical calculations in this restricted space where we got rid of many space because they're exponentially complex. So all these systems give rise to multiplets in the excitations, to in-gap states, to orbital selective Mott transition. This is if we have two orbitals, one orbital can be metallic and one orbital can be a Mott insulator, for example. I mean, they're interesting behavior. So we have to deal with Hamiltonians like this. What do we have here? We have, for example, the Hamiltonian has a hop-in part. Let's look at it here. I prefer to look at this and not at the equations. Here we have 1, 2, 3 orbitals. Each orbital has its own hop-in, T1, T2, T3. In each orbital, we have a strong on-site Hubbard type of interactions. When we have two particles, we pay an energy U. This is a Coulomb interaction. We're not going to take a long-range Coulomb interaction. We take it on site because it's an approximation. We can also consider the extended Hubbard model, where, for example, we here for two neighboring sites, we pay an energy V. It's not written here. We can also pay an interorbital interaction U, and also a Hund J, because I mean, if here we have several orbitals in one atom, we have a Hund J. So all these, here we have the hop-ins, the chemical potential, and here we have all this complex interaction. This is called the Kanamori-Hubbard type of interaction, and many people are working with this. Antoine Georges, Gaby Kotler, and I mean, it's very interesting because it shows many of these interesting properties. I said I wanted to go to physics, but I need to do one more thing of a method, because I mean, these systems are good to study with the DMFT. The DMFT is dynamical mean field theory. It is a mean field theory, but it works very well for correlated systems. This was, I mean, there's a good review of modern physics written by Antoine, Gaby Kraus, and Marcelo Rosenberg, and also Dieter Vollhardt, and it was involved in the beginning of the DMFT. What is it? We have our system. Our system is all this, the bulk. We pinpoint one site because we're going to do a mean field a la Weiss. We get one site. This site is what we're going to call the atom or the impurity. When I say impurity now, I mean one site of the translational invariant system. It's not an impurity. It's with this particular site I took, but all the sites have interactions, okay? Now I call this impurity. It's not a real impurity. This atom or impurity now is correlated, is interacting with an effective medium. It's all the rest, and it's interactively. We have to calculate the effective medium to be able to represent the system correctly, and this is done iteratively until you converge. So the main approximation is that the self-energy of the correlated electron is local. I mean, we have a local self-energy, and this is an approximation. If you want to have a self-energy due to interactions which is not local, then you have to take, instead of one atom, you have to take here like a cluster and consider this as the effective impurity in the DMFT. But now the DMFT is this. I mean, I don't want to go into details, but what you start with your iterations, the self-energy is 0, and then you calculate the Green's function. You calculate the Green's functions as 1 over omega minus the hop-in minus this 0 self-energy. You get an effective Green's function. Then you define the hybridization that you call gamma. I mean, this is a technical thing. I won't go into this because they are the iterations of the DMFT. But at some point, you have to put in the correlations. And when do you put the correlations? When at some point you have to calculate the Green's functions at the impurity site. Okay, so if we go back, with all these iterative equations, at some point you have to calculate the Green's function of an impurity with an effective bath. The bath goes changing. You change the hybridization to the bath, you change the local energies, but the bath is non-interacting. But then the bath goes changing to be able to give you the result for the many-body problem. And this converges for the infinite. For the infinite is shown, it's exact for the infinite dimensions, and in this approximation. So doesn't matter the rest, but the important thing is that we need an impurity solver. It's called like that. You have to calculate the Green's function for the impurity. And this is where we have to use a many-body technique. It can be numerical, it can be analytical, etc. Once you get the impurity, the impurity Green's function, then you go back and you can calculate until convergence. There have been many impurity solvers because that's a many-body and the bottleneck of the method. Iterative perturbation theory, exact diagonalization, Hirsch-Phi quantum Monte Carlo, non-crossing, NRG, so numerical organization group. And then more recently, I mean, this is in 2004, 2005, we came up with the DMRG as impurity solver. And this was good because it really improved the precision a lot. But then there were other people in Germany who also followed, and now many people are using the DMRG as impurity solver. But most of the people are still using quantum Monte Carlo. Now, let me just tell you one technicality because it's important to show why we have more precision. We want to calculate the Green's function of the impurity. This Green function is a complex function, okay, defined on the complex plane. So we have the real part of the Green's function and the imaginary part of the Green's function, and each of those parts are defined on the complex plane with omega and E omega. Okay, so the complex plane means that here we have the energies omega, and here we have the Matsubara frequencies I omega. And then on top of this, we have the real part and the imaginary part of the Green's functions. We have to calculate that object. Now, what quantum Monte Carlo does, there are several methods based on Monte Carlo, is they iterate, but always, but they converge in the I omega axis. So they converge on this axis here. Once you converge your Green's function on the I omega axis, as the functions are holomorphic or analytical, you could in principle analytically extend this complex function to the real axis, because we want to calculate the response functions on the real axis. This is the density of states, etc. Okay, the response functions are here. So you can analytically continue these functions to real omega. The problem is that is an ill-posed problem, because you converge. The convergence here is an approximate convergence, and the functions on the Matsubara frequencies are very mildly behaved. For example, if I plot something in I omega, they're potatoes like that, okay? And then you have to take this potato here onto the real axis, and here you have to try to get things that have gaps, that have, etc. How do you get this from that? Because you're losing a lot of information. The positive thing of Monte Carlo, quantum Monte Carlo, is that they are able to calculate with finite temperature, and we are not. We could in principle, but it's very complex. So what we do is with the DMRG, we converge directly on the real axis. We don't converge on the imaginary axis. But as we have a finite system, the finite system is my complex impurity. Remember, this is replacing all the interactions of the system. And we have a non-interacting bath. Let me write it like this. This has a local energy, EI, a lambda I. So this is a non-interacting bath, and this is an impurity. So we, as the system is finite, because we put in a finite number of bath sites, with the green functions, we have delta peaks. It's not a continuous, it's delta because it's a finite system. So then on this axis, we really have delta peaks. But to get in so then we broaden the delta peaks by a Lorentzian, and that means that we are converging slightly above towards the I omega axis. So we're including a omega plus I eta, which is slightly above. So then the Lorentzians become a little bit broad. Technical question, doesn't matter. Well, so this is much harder to converge here, because you need to keep much more information, but it's much more precise. Now, let me compare with NRG. NRG also converges in the real axis. But numerical romanization group, which many people are using now, the NRG is tailored to solve the impurity, an interacting impurity, like the Condon model or the Anderson model. Okay, the NRG was developed by Ken Wilson in 1964. And what you do is a logarithmic discretization of the energies, and you really focus on what's happening close to the Fermi energy here. So let me forget about this. Now let's look at the density of states. This is the density of states as a function of energy. So here you have the Kondo peak, and here you have the upper Hubbard band, the lower Hubbard band, and the NRG is really tailored to look at to see the Kondo peak, but it's not good at higher energies. With the DMRG, we are good at higher at all energies, at a cost, because we are reducing it's not a perfect method, okay? But it's in that sense, it's better. And also, in addition, the quantum Monte Carlo has the fermionic sign. You can get rid of the problem of the fermionic sign problem of the Monte Carlo. Monte Carlo, when you exchange two fermions, you don't put the -1. And that's a terrible problem for Monte Carlo. So that's a famous fermionic sign problem. The advantages then with DMRG solver is you converge on omega, a real omega axis, all frequency scales. We can put arbitrary interactions, so it's not perturbative. No sign problem like the Monte Carlo fermionic sign. We can use large baths. These non-interacting baths can be large. We can take large systems. We can consider several orbitals, so a complex impurity with several orbitals. Several sites of the impurity, so then we can get a K dependence on the self-energy and finite temperature. Nobody did it yet. It's an open question. And this is what we get. Now I'm still showing you these figures. These are different systems. For example, the top one is one impurity hybridized with a bath. You see, it was like this, but what I did is I put all this into a one dimension, okay, like this. It's the same, but with a different topology. So this is an impurity hybridized to a bath. If we have two impurities now, or a complex impurity, each, for example, a two-level system. This is, for example, describing the two-orbital Hallberg model. Why? Because I have an extended, so we have the bulk system. Every site has two orbitals, and every orbital has the U, the V between the orbitals. If we have a hop-in, now, so then one impurity has two orbitals when I do the DMFT. So here I have the two orbitals and I have the non-interacting bath. So then I can also take four orbitals, or I can take a one orbital Hamiltonian, but consider four sites for a non-local self-energy. And so the things are complicated like this. And this is where we have to use a DMRG. This is where we have to apply the method to, all this complex thing. And this is the Hamiltonian. And so we have to calculate the dynamics with that. So now let's stop with technicalities, and we're going to talk about physics. We haven't studied the three orbital Kanamori-Hallberg. We studied the two orbital Kanamori-Hallberg. So here I have one orbital, orbital 1, orbital 2. I put two different hop-ins, T1 and T2. The hop-in here is much larger than the hop-in here because we want to see orbital selective MOT. So then we have local U. And we also have an interorbital J-Hund and U2. I call it U2 or V. I mean, it's an interorbital interaction, which is important in this system. It's not one-dimensional. I draw it as a one dimension, but it's a DMFT for a square lattice. So what do we get? Now we use the DMFT for that system, for the doped system, and we see this. Let me just explain. So here we have, remember, orbital 1, all the band 1. This is the band 2, which is much narrower. And we found new states here. We found new quasiparticles, which was a surprise, but thanks to the precision of the DMRG as impurity solver of the DMFT, we could find these in-band states. How do we interpret this? Here we have, these are all densities of states for different values of U, of the local U. We have a local U, but we also have what we define a delta, which is a difference between U and the interorbital U2. So now let's look at this case. When the local U is very large, we have, this is the frequency, the energy, this is the Fermi energy. When U is very large, we have an insulator because here we have the upper Hallberg band, the lower Hallberg band. The Fermi energy does not have density of states, so we have a gap. This is an insulator, okay? Now here we have two densities of states, and each one corresponds to a projection onto this is the red one is a projection onto the wide band, and the black one onto the narrow band. So this is orbital 1, and this is orbital 1, and this is orbital 2. Both orbitals are insulating. But look what happens when we have an intermediate. When we put lower U is 3. We have the upper Hallberg band, the lower Hallberg band. One band becomes metallic. Now we have a finite density of states at the Fermi energy. So the red band, the top band is red. The red band is metallic, but the black band is not metallic because the hop-in is very low. But in the density of states of the lower band, we have these two peaks whose weight is exactly half of the weight of the top band. Now, what does that? So we didn't understand it. We saw it, and we didn't know what that was because these are in-gap states. Well, now, when we go to very small u, you see now at the Fermi energy we have density of states, finite density of states for the black band and for the red band. This is an artifact of the finite system, the dip. So now the two bands are metallic. This one is much less metallic because the quasi-particle weight of the carrier is much larger in the white band, which is the red, and this has a small quasi-particle weight, so the bandwidth is very, very narrow. This is the upper Hallberg band, the lower Hallberg band, and now we have not only the quasi-particle of the black band, but we also have a little tiny quasi-particle in the top band. And now these are two different kinds of quasi-particles, and we have identified them as Holon doublon quasi-particles. So let's look at this one, it's easier to understand. In this case, remember we have a metallic orbit band 1. The top band is metallic. The lower band is insulating, okay, because it's a black one. What these are, this peak here is the density of state. So I create a particle in band 2, and then I evolve in time and I destroy it. That means that there is a weight at this energy. Let me just tell you that when delta is when U2 is 0, so when there's no interorbital repulsion, so if there's no interorbital repulsion, we have two independent Hubbard chains, not chains, 5. Yes, I'm finished. We have two independent Hubbard lattices for U2 equals 0 because U2 is the repulsion between the bands. So then we would have a Hubbard band here and a Hubbard band here. When we put this interorbital interaction here, what that does is it transfers weight from the upper Hubbard bands to the in-gap states. Because now, if we look at the difference, this is the top, let's see in the local atom approximation. This is the orbital 1 and this is orbital 2. The ground state is something like this, let's say, a particle in orbital 1 and a particle in orbital 2. Now, an excited state will be 2 particles in orbital 1 and 0 particles here. This costs an energy U, because you're paying a local energy U. If there's no V here, this costs energy 0. But if we have a U2, this costs energy U2 because it's an interorbital. So an excitation to go from here to here costs energy U minus U2. So what I'm doing is that I'm changing the 0 of the original state, and this is why now with the interorbital interaction, I'm transferring weight from the upper Hubbard band to there. So this hasn't been calculated before. We observe it because we had it more precise calculations. I won't go into these details, but you see this exact projection here. This is because we really we're calculating the response function of creating this quasi-particle, which is, I create a particle up where there is a down, and there is a hole in the other orbital. So I'm really creating a Holon doublon excitation. I'm creating an excitation like this, and this is what we call a quasi-particle. Okay, so this operator here creates this excitation, and the dynamics of the response function of this excitation is exactly these blue peaks we find here, and they really coincide with the quasi-particle peak. So we were able to explain the nature of that excitation. And then, of course, once you find something, then other people, with other methods, you know that things are there and you can find them. And then Gabi Kotler with his postdoc, they calculated using a slave spin method, and they find the density of states. They find these in-gap states. And this is their method compared to ours. Ours is a continuous line, and the slave spins are these lines. So they really now start finding it with other methods. Also, Weichselbaum and Kotler and others, they also calculated now using NRG for a 3-band model where we have orbital 1, orbital 2, and orbital 3. So we have 3 orbitals, 2 of them are degenerate. One of them is a metal, you see the density of states, and this other one here, the red one, is the insulating orbital, and they find these structures here, and these are the Holon doublet excitations using NRG as an impurity solver of the DMFT. Okay, so this was interesting. And one last thing is a very interesting concept, and it's because now we have a different liquid in the system. Why? Look, these two curves. What am I plotting? This is Z, the quasi-particle weight, as a function of the interaction U. If the interaction U gets very large in this system, the quasi-particle weight has to go to 0, because, I mean, for example, look, these are 3 different ratios of Hopkins between T1 over T2. The blue one is when the T2 is half T1. So we have a very large quasi-particle, and it goes, the critical U is 4, above which the system is an insulator. But now look at the ratio of, this is, T2 is 1/50th of T1. So the Hopin here is really very, very small. It's a nearly flat band, okay? And we have this red curve here. But if we look at the quasi-particle weights in band 1 and in band 2, they're exactly the same. And it's strange that the band 2 has a quasi-particle weight, because it really should be an insulator. The problem is that because the system has now this U2 equal to the local U, we have a locked metallic state. So even if band 2 is very, very narrow, if we have mobile holes in band 1, these holes couple to doublons in the lower band, and they produce mobile charges in band 2. So the movement is like a drag effect, that holes in band 1 are really moving doublons in the other band. And this is why we see an exact locking of the metal insulator transition. So here we do not have an orbital selective mod case. And because there was a very long controversy between different groups, Manfred Sigrist and other people, Manfred was right. There is a lock-in of the situation. No, so I won't go into details, but these are other densities of states now for the doped system, because I just showed you the half-filled system. In the doped system, we have the upper Hubbard band, the whole doped lower Hubbard band, and we have this Holon doublet states appearing in the middle when we have. So now we really see this in-gap states in many different situations. And then we wanted to get rid of the local approximation of the DMFT, and we said, well, let's calculate it on 1 dimension. 1 dimension, now this is really 1 dimension. We have the upper band, the lower band, and in 1 dimension, you know, at the critical value of U is 0, because as soon as you put U, it's a Latinger liquid, and it's a transition. It's an insulator for the half-filled case. So then we had to go to the doped case, and we looked at this system in 1 dimension. And in 1D, we also find the Holon doublet state. You see, this is again the density of states. This is the Fermi energy, and the upper Hubbard band, the lower Hubbard band. And when we dope the system, look, this is for 0 doping, okay? So it's a half-filled system here, the upper Hubbard band and lower Hubbard band. As soon as we dope the system with holes, ploop, we have the Holon doublet band, because one of the bands creates holes, and these are accompanied by doublons. So, well, I mean, this is again to show that. So conclusions, to conclude then, the complexity of correlated materials, they require sophisticated and precise numerical methods to unveil the microscopic details. We have developed the precise method is using DMRG as impurity solver of the DMFT. The DMFT per se is interesting. And now with a good impurity solver, it's even more precise. And what we're doing now is we're including information of DFT, Klaus, because now we want to use the dispersion E of K, epsilon of K, of real materials, and then we can use a DMRG. So now we're doing this with my students. Any ideas are welcome. So this led us to find a richer structure in the local density of states, the in-gap states that hadn't been seen before in these complex models. And in particular, we find the interband Holon doublet excitations, which are clearly visible in the DMFT and in 1-dimensional models. Thank you for your attention.